I answered it and we had a, oh no, it's not going to go so well, is that? Yes, yes, I will control all. Yeah,
which is the radius.
True.
They do something.
That also when the mass term is destroyed, it's irrelevant. You get the anomaly seems completely irrelevant. It seems like just
Well, it's still symmetry.
well, that's true, but like the yeah, but
No, what would be nice is if there were a situation.
Basically, it's like it's like you overlay the transfer lattice and you overlay mathematical triangle, and then they can tune conditionally from triangular to calculate. Yeah. But in their case, it's like the depths of the window, not the door directly. It's like if your depth is very shallow, then it's basically
Yep.
yes, yeah, one has to one can imagine adding a master.
It's like really.
And then of course that thing has some dimension. Something. Hello? Hello? It's getting the cosine phi. Yeah, honorable. Sure.
Okay, great.
Why there'd be a why there's 0%.
Great to introduce this person who doesn't need any introduction. It's a great pleasure to welcome Professor Wiegmann from the University of Chicago, and Frank Institute from Canada Center, and from Enrico Fermi Institute. If I'm right, with all the it's all around the university. So anyway, Paul is the person who is extremely well known in both condensed matter community and to high energy community. And he is a person who solved exactly all the sigma models. The person who with Polyakov solved the Wiener model, and the person who solved exactly multi-channel quantum model, for which he got Sager Prize in 2017. And he also solved the Anderson model with magnetic impurities. So all are exact solutions using beta and delta. And he did many different things and got a number of prizes, of which Sager Prize is one, Humboldt Fellowship is another, and there's a list of other awards, mostly from European institutions. So it's really great to welcome Paul today. He will be talking about quantum anomalies as kinematic properties of a classical fluid. And before I stop, let me quickly tell that there is a schedule for the rest of the day. However, if somebody who's not on the schedule wants to, it's around this afternoon and try to arrange a little bit and
Thank you very much. I understand that it's for some of you, it's a second seminar right after another. I'm impressed your strive to knowledge. Very impressive, but my apologies. Okay. Maybe there's a pointer. No? Yeah, it's better than pointer.
I can get one downstairs.
okay, good.
Okay. What I would like to do today is, well, as always, discuss the most recent works. And these days, it's about hydrodynamics. And it's unexpected, surprising, maybe, I don't know how to call it, relation to anomalies chiral anomalies in quantum field theory. It's the story is based on a series of papers we wrote with Sasha Abanov from Stony Brook. So I will talk about two seemingly not related, but oh, fantastic! That's great. Thank you very much. That's a real one. Okay, I will talk about two fundamental problems of physics. One is the Dirac equation. I wrote Lagrangian because it's shorter, but Dirac fermions. That's a quantum problem. Well, all the story which I will describe is in 3 spatial dimensions and 1 time. So my first subject is Dirac fermions, or quantum electrodynamics, if you wish. Quantum. And the second subject is Euler equation for fluids, for classical fluids. Quantum, classical. This fermions coupled with electromagnetic field, and that is a fluid, classical fluid. But I couple it also to electromagnetic field, so it's plasma. It's called plasma. So assume that fluid is charged. It's not important, really. Instead of magnetic field, I may assume that fluid is neutral but rotating. Magnetic field and rotation, same thing. Then it will be called Coriolis force. If it is magnetic field, it's called Lorentz force. Not a problem. No, it doesn't matter. And apparently there is a, as I said, unexpected and rather deep relation between kinematical properties of these two problems. And I assume that in this audience, this problem probably is well known. It's quantum electrodynamics. What could be more or less more familiar than that? About hydrodynamics, that's I'm not sure. Hydrodynamics is not part of the current curriculum of theoretical physicists. And knowledge of hydrodynamics is not common in those audience. Maybe in across the street in engineering department, people know more about hydrodynamics than in physics, it's a shame because it's one of the most beautiful and most developed and deep subject of theoretical physics. So, but I will slowly progress through it, assuming that knowledge of hydrodynamics is not common. Some people think that it's simply about plumbing, but it's not. It's about geometry. It's quite important to understand that when we say hydrodynamics in physics department, we mean geometry. This point of view on hydrodynamics has been popularized by Vladimir Arnold in 1960s, but it's kind of belong to mathematical side of people who study hydrodynamics is either mathematicians or engineers. And it's a shame. In this point of view, I will develop. Now, relation between these two is quite familiar in one spatial dimension, and then there is a full correspondence between Dirac fermions and hydrodynamics, but in one dimension, both quantum. That is called by Bosonization, and it's unfortunate misrepresentation of the phenomena. Instead of Bosonization, we have to say hydrodynamics. Electrons in one dimensions always form a fluid. If there is small interaction, they always form a fluid. Fluid must be described by hydrodynamics. Now, in 3+1 dimension, it's not always the case, but sometimes fermions also form a fluid. Under certain conditions, Dirac fermions form a fluid. One of the most famous examples is helium-3. Isotopes of helium-3 fermions, and it's a superfluid. And once it's another example, which is nowadays quite popular, but less established, is quark-gluon plasma. So very fast, very strong collision between heavy ions produce for very short time produce quark-gluon plasma, and there are certain conditions when this plasma has to be treated as fluid before quark goes. So sometimes it's happened, but Dirac fermions has a very characteristic properties which is called quantum anomaly. It's a kinematic properties. It is property survive interaction. It's tolerant to whatever interaction. It's not dependent on interaction. It's a property of the Hilbert space, and it's a observable property, one of the most fundamental aspects of quantum electrodynamics. And once fermions form fluid, this property must inherit by fluid, must be seen in fluid. When I say the word fluid, I mean Euler equation. Fluid and Euler equation, the same thing. If I say the word fluid and it's a non-dissipative fluid, then if fermions form fluid under certain conditions and fermions exhibit anomaly as its fundamental property of Hilbert space, fluid must somehow show the same property. Is this true? And how does Euler equation reflect anomalies? That's the subject of the talk. I will appreciate questions from the as I'm going. But that's a motivation. It's a very old question, sort of simple. So if you open, volume 5 or 6 of Landau hydrodynamics, it's the largest volume possible for a reason. The fat volume, the biggest for a reason, very deep subject. This property has not been discussed there.
Right. When you talk about fluids, do you have in mind relativistic fluids?
No, fluid is fluid. It could be relativistic, it could be non-relativistic. If I would like to compare with Dirac thermals, which are relativistic,
Yeah, that's why I'm asking.
perhaps I have to consider relativistic fluid. But the story which I'm going to talk about have relevance to fluid. And it's the same, relativistic, not relativistic.
It's very interesting because in a Dirac equation, to get to a non-relativistic form, you need a mass. But if you turn on a mass, you destroy chiral symmetry and then you destroy the anomaly.
Right. Well, it's not destroys the anomaly. It's means that anomaly is not visible in all scales, but at energy higher than mass, it's still there, right?
But then, okay, fine.
Yeah, yeah. But let's assume that there is no mass.
Okay.
Mass means gap. Fluid usually, by fluid I mean water, literally. So, next time we clean our hands, my hands, I encounter fluid. There is no gap in fluid. If you open faucet, it's easy to excite. So perhaps correspondence would be without this.
Okay.
The correspondence. Okay. So this is my Euler equation plus forces, electromagnetic forces. I assume that it's charged. And Euler equation has two, and hydrodynamics in general has two aspects: dynamics and kinematics. Dynamics, perhaps very interesting, but almost impossible. Dynamics of fluid is pretty complicated. But apparently kinematics of Euler equation and the fluid is a very interesting and very deep subject itself, without even solving equations. We may discuss kinematic properties of the fluids, and that's the subject. Kinematic, so Euler equation, perhaps one of the first partial differential equations written by mankind. It has, it's as old as one can think, written by Euler, presented in Berlin session of Academy, session of Berlin Academy in '52, published 5 years after. And since then, there are certain steps of developing or understanding kinematic of fluid. Of course, it's Kelvin, but a pretty big gap. It's almost, it's more than 100 years. Then there are two scientists from the city of Odessa, a French differential geometer, Lichnerovich, 1940, and Vladimir Arnold, Russian mathematicians, 1966, but they have a common ancestor city. Next step is Carter, and their ideas have been further developed by Carter, let's say British mathematician, and finally by also British physicist Moffat. And I will follow this development and add one more piece to this role. But let me start from something which is more familiar, which is Dirac equation and the quantum axial current anomaly. So I will review the simplest known things and then go to hydrodynamics. I start with something which must be familiar. So Dirac equation, Dirac fermions, has two chiral components, left and right. Generally, it's a spinor with it's a multiplet with 4 components. 2 of them left and right chirality, and another is spin up and down. So I'm most concerned on left and right and sigma the spin. So I will couple the Dirac equation with Dirac fermions with abelian gauge field. And then notice that written in components, Lagrangian Dirac equation, as well as equation Lagrangian Dirac fermions, as well as the equation itself, is completely decoupled to the motion of the left particles and right particles. Sigma is a Pauli matrix describing the spin. So classical equations are decoupled by two, and it's based on the fact that spinor representation of rotational group in 4 dimension is reducible. Once it's decoupled by two, there are two currents which must conserve due to obvious gauge invariance, two neutral currents. One is called vector current. It's simply current of number of particles, which consist of left movers and right movers. But then axial current, which is the difference between left movers and right movers, which is called chirality, is also conserved classically simply because equations is decoupled, we don't know each other. Sorry, I'm telling you kind of trivial story, but it becomes non-trivial very soon. In 1969, Adler and Bell and Jacquif, this is 2 papers published in the same volume of Physical Review Letters, discover or explain that in quantum case, things are different. Namely, the current, vector current, which describes simply how many particles in the system, is indeed conserved, and that's a consequence of the gauge invariance fundamental principles. The system is isolated. Number of particles can move, but the number doesn't change. This is the number. But the chirality, the difference between left movers and right movers, could change in time if a product of E and B, if E has component parallel to B, and this integral is not 0. Then the number of change in time. The process when electric field and magnetic field have parallel components, sometimes called instances. And if these instances occur, the number of the difference between left and right movers shifts to if particles move to the right, and then there is certain process of instanton which produces E and B. It's turned to the left. Therefore, the total number of the difference between them, between number of right movers and left movers in this case, will be changed by 2, or maybe by 4, or actually by 2 times the integer. And integer here is the number of instances. That's a pure quantum effect. There is H bar here. And it has local form. Local form is here. There are 2 currents, but axial current, difference between left movers and right movers, is instead of being conserved, is proportional to E and B with the coefficients K, which happen to be equal exactly to later on, it has been recognized that this 2 is a Chern class. It's a topological number, Chern class of a certain fiber bundle. I will not talk about it. Initially, it has been computed by diagrams, through diagrams, but really does not need to be computed. It has to be understood as from geometric point of view. In books, in textbooks, it's computed through triangle diagrams. Triangle diagrams describe that process. It has two photons and one fermion here in the nearest order of perturbation theory. This triangle diagram contributes, it actually computes this K. And if we compute it literally, the diagram diverges. So it's actually equal to infinity and need to be regularized. It could be regularized in many different ways, but it has to be regularized such that the total number is conserved. Gauge invariance. Once it's done, then there is only a unique answer. And answer is that the diagram which is supposed to be infinity is actually equal to precisely 2. As I said, the modern understanding is such that it doesn't need to be computed through diagrams, also if done in every textbook. It has to be understood from geometrical points. Now, this is how it's done. There are many ways of doing this, but the issue is to regularizing of gamma 5 Dirac matrix in a gauge invariant manner, either through his kernel, as it's written here, also zeta function regularization, many different ways. The result is that this number is, and physically it's very simple. If integral of E and D is happen to be 1, then one right movers decided to go left by and changing this difference by 2. Fundamental phenomena has been observed, and is responsible for many applications, physical applications. So they summarize this here. Now, if I integrate it over time, that will be integral over what is called Chern-Simons, abelian, all abelian, change from during a process of instanton from 0 time observable time. That's what it happened. This number itself, which count number of instanton, has interpretations, geometric interpretation. Think about magnetic field as magnetic lines, which in quantum world supposed to be Curie quantized magnetic flux. Magnetic flux. Then consider a link between two magnetic lines. One magnetic tube and another magnetic tube. The linking number is precisely this integral. So what the anomaly really means, it means the following: that number of right and left movers are intimately related to the linkage of magnetic lines. So this particle lives in external magnetic field. Magnetic field has this may have this property, and if I start from configuration which magnetic lines are not linked, and do something with my apparatus, making them linked, one right particle decided to move going left. That's the essence of anomaly, right? So this is obviously integer number of right minus number of left. This is also integer number. How many times magnetic fields is linked? If you change one, another follows. This coefficient 2 tells me that the total number of particles is the same, but simply one change direction, right? The story has a long history, generations, since late 60s work on it, computed in different way, but really there is nothing to compute, although it has been computed through diagrams, regularization of word identities, but that's simply reflecting the property of the Hilbert space of fermions. If we add interaction, literally nothing happens. That's property higher order diagrams do not contribute. And this fact simply is not related to interaction. Okay. So I skip this slide. Okay, now let's me come to hydrodynamics, Euler equation. Well, it's a fluid, and possibly I will jump from non-relativistic to relativistic case. Formulas are more easier and nicely looking in relativistic case. But some other formulas are better looking in non-relativistic case. But really, the story is not related to a metric. Minkowski metric, Galilean metric, it's about differential forms, not metric. So that's why I will jump. For example, that's hydrodynamics for non-relativistic fluid. It's of course, it's Hamiltonian, of course, has kinetic energy and potential energy. If potential energy depends only on the density, such flow is called barotropic flow. This is always the case which you can see. Then this Hamiltonian together with Poisson brackets classically produce two equations. One is the continuity equation, conservation of mass current. And another is dynamical equation, Euler equation. It's coming from that simple Hamiltonian. Okay. It's not immediately obvious why from such a simple Hamiltonian, a Newton equation will get that form. It's all hidden in Poisson structure of a fluid. And when I say the word fluid, I mean a certain Poisson structure. This Poisson structure produces this equation. Okay. Now, so equations, the system itself has one obvious conservation law, current. But apparently, it has another conservation laws, which people are less familiar, but it's a literature fact, and, sort of well understood, but narrow corner of the literature. There is, in addition, there is one more current, which I called X current, and hydrodynamics is called helicity. It's a falling current. I write it, if I will write it in many different ways later on, but let's P be momentum of the fluid. And then from momentum of the fluid in 3+1 dimension, I may construct three form, which dual is a pseudo vector, axial vector. That is called helicity. And it so happens that as a consequence of these two equations, the helicity current is also conserved. So this is dynamical equation they produced from this Hamiltonian. Conservation of continuity equation may not be called dynamical equation, but it's a neuter, conserved neuter current due to, say, gauge invariant, global gauge invariant system symmetry. But apparently there is another conserved current, which is the constant. Moreover, equation itself depends on the equation of states, energy as a function of density, from which we read pressure, but this conservation doesn't care what kind of interaction between particles. And it's apparently a kinematic consequence of what we mean by saying the word fluid. When we say the word fluid, we mean something. And it's not very clear what do we mean. But mathematicians haven't understood. And this is what we mean, this conservation. And I'm going to explain. So like in quantum electrodynamics, there is also two currents. One is vector current. It's a simple current of mass, and some strange current, maybe new for many of you, some of you, which is called helicity, which is pseudo current. It's a pseudo vector. It's not a vector, it's a pseudo vector or axial vector. It's also conserved. Right. So the story which I'm going to tell you in the remaining time is that if I add electromagnetic field to that equation and demand that mass will remain untouched, number of particles doesn't go away from the system, then this conservation will remain. But conservation of this helicity changed by electromagnetic field, and it changed precisely like in quantum Dirac equation. This is classical.
So in the relativistic context, I know what P0 would be, the zeroth component of the moment.
Right.
What is it here?
Yeah, good point. In non-relativistic context, it's a little bit, that's why I'm jumping from formula to formula. Absolutely. It's this P naught in non-relativistic context will be what is called Bernoulli function. It's a square of velocity plus chemical potential. And definition of chemical potential is pressure, gradient of pressure equals density by chemical potential. How much energy change if I add one extra particle? That's chemical potential. And this P naught has a bit strange form, but in the relativistic case, it's four vector, one of the components of the four vector.
And the derivative with respect to this D0 is
formula,
dt, right?
This formula remains,
Okay.
because this formula built out of forms, differential forms.
Sure.
It doesn't care about metric. So the space may be curved. Formula remains. Okay. Now let me say few words about helicity. What is helicity? And let me do it non-relativistic in non-relativistic. So I have momentum. Momentum is for ideal fluid is mass time velocity. From this momentum, I can form that interesting combination, which is a pseudo scalar. I can integrate it, and that will be global helicity, what is called global helicity. This is local helicity, integral, three-dimensional integral, space, local helicity. It so happened that this number never changed. When it's done, when it's set initially, it will stay there forever. That's I'm going to explain. And it's happened regardless of the Hamiltonian. So it's not a story about dynamics, it's a story about, in quantum case, I would say Hilbert space. In classical case, I would say, what do we mean by fluids? Okay. Moreover, so this conservation of this current, axial current, helicity current, is not a Noether current, not related to any global symmetry, like conservation of mass. Okay. So now helicity could be visualized. Advantage of hydrodynamics towards quantum field theory is hydrodynamics can be visualized. So I can present you pictures, and some of those pictures are absolutely beautiful. In quantum field theory, pictures are, apart from Feynman diagrams, it's difficult to draw pictures. Okay. So, first of all, that object is, suppose now my classical fluid becomes a superfluid. Then this object happened to be quantized. Let me explain. There is an Ansager quantization, 1940, who said that circulation of momentum is always quantized in units of Planck constant. What that means? It means that if there is a vortex line, then fluid circulating around vortex line, circulation is this integral. It could be always quantized. It must be always quantized. Okay. That if the fluid is quantum. But even if it's classical, there is some remnants of it. Euler equation allows vortex line with zero core, almost zero core. It's called weak solutions, but the differential equation doesn't mind these solutions. It's a singular solution, but it's considered to be okay solution. So it's vortex line, but core is zero. There's no parameters. Okay, and it could be experimentally realized. Of course, experimentally, it's this experimental picture. The experimentally core is not zero, but it could be small. And Euler equation has interesting property. So if we create a vortex line which is linked, this has been realized very recently, maybe 7 years ago, actually in Chicago, by William Irvine. So create vortex line which actually linked. It's called trifold link. Initially, I created it initially, and then it lets it go. Question: would it be unlinked ever? So can this line cross that line? The motion of Euler equation is always turbulent. It's a complicated motion. Computer doesn't know what to do with Euler equation. Very nonlinear. Many things happened. Question: if I linked vortex lines, like in this picture, will they ever unlink? What do you think? It's a question of this question it has to be addressed to simply a differential equation. There is a differential equation. I create that configuration, let it go. Many things happen, turbulent motion, complicated motion, but can vortex line cross each other on links? Apparently, it's a consequence of this equation, a very deep consequence, that they will never unlink. Classical. Right? So it's not really a differential equation. It's a geometric statement that vortex lines will not link. And there is also vice versa. If you tell me, write me a differential equation with minimal order of derivative, Hamiltonian such that vortex line will not unlinked, this is the only one. It's almost equivalent concept. There are some questions. Okay, so configuration change very dramatically. That's initially that's some number of seconds later, but never unlinked. In reality, it's of course unlinked, but only due to viscosity. Viscosity will destroy everything. It's a Hamiltonian property, but for some time, for good fluid, with low viscosity, water is a good fluid with very low viscosity. Configuration of vortex line change, but they don't want to unlink, but they eventually unlink.
Pasha, in this respect, your definition of fluid is what? Is it without viscosity?
Yeah, I mean non-dissipative fluid. When I say fluid, means non-dissipative fluid. Viscosity change many different things, but if you understand fluid without viscosity, adding viscosity, it's a piece of cake, right? So this property follows. But first, we have to understand what Hamiltonian system.
Kind of low battery.
Moment, I am prepared. Okay.
So many things.
Wait, one more addition to this slide. One more addition to this slide. This property tells me that classical differential equations knows about integer numbers because linking number is integer. How come? It must be very surprising that this differential equation knows about integer numbers. It's classical. Would it be quantum? Then, of course, and circulation is quantized. Then we notice that this object also quantized in units of h bar square. One circulation and two movements square. And the coefficient which stay between them is exactly the linking number. When we write helicity and integrate it, we obtained a linking number times square of circulation of vortex. Classically or quantumly, it's like that. And that's why it's conserved, because linking number is integer, it cannot be changed continuously. Right? So once it's set it will stay there.
I have a question. So said that helicity equation is from can be given from some classical equation, but why do you have this benchmark?
Classically, helicity is proportional to linking number times circulation of fluid around a vortex. Would it be quantum? This circulation is quantized in units. Well, classically, you give me a circulation, then it will be stay here. But integer numbers are still there. Classical quantum. That's my. So this helicity could be visualized another way, apart from linking number. It's also tornado. So all these tornadoes has a given helicity. So the movie how fluid flow is with helicity is the following. So there is a vortex. Vortex line, fluid circulating around vortex line, going around. But actually, this component along vortex line itself and eventually spiraling. So helicity is related with the pitch of the spiral. Right? So here's a spiraling. It's a vortex, but there is also, as you can see, this configuration of his. There is also Arnold theorem, quite famous theorem to Arnold. It says, show me the stationary solution of Euler equation. That is Euler equation. And I would like to find stationary solution, which means that I throw away this time derivative. And these solutions are classified, and they are all in classes, and each class classified by helicity. Stationary solution of Euler equation fall into classes of a given value of helicity, which is a number once given stays there, and within this class I can find stationary solution. This example of stationary solution, of course, it's moving sort of but slower. Fluid moves much faster. Okay. So, mystery of conservation of helicity in Euler equation has many faces. One of them is so-called variation. So this is an example. It's mathematical foliation is a mathematical concept, which says that flow could be thought as surfaces of vorticity, closed surfaces, so-called integral surfaces, and these surfaces fill the entire space, depending on the initial data. This is example of foliation in geology, right? So it's a bunch of kinds of lines which fill the entire space, making no holes. Conservation of helicity is related to the fact that flow is foliated. It's one geometrical characteristics. On this slide, I derive conservation of helicity starting from Euler equation, but I don't have time. It's a short slide. It's very compact. Derivation obtained relatively distantly. It could be presented in this audience, but I don't have time for it. This is my Euler equation, and that is I derived conservation of helicity. It's a beautiful derivation based on which belongs to Lichnerovich, 1914. Based on the fact that Euler equation could be written in the form which equivalent to so-called Frobenius condition for foliation. What foliation means? Let me explain. If I have a flow, a fluid move, but it never make an empty space, right? Gas can make empty space, but fluid cannot, right? So it's an example that there are some interesting property, what we mean fluids. And then they reflected in this Frobenius condition from which foliation it follows, but I skip this. Okay. And I have 5 more minutes.
You have 10 minutes.
10 minutes. Oh,
Too much.
then if I take 2-3 minutes, I will come to this derivation and show you how things work once understood. If you try to derive conservation of helicity, I did it myself before I learned how to do this. It's an algebra, right? You write this object. You write this object and start to differentiate in time. But you know how momentum being differentiated in time looks. It's an Euler equation tells you. So you substitute it here, you substitute it here. 5-page algebra. Then you discover that everything can. It's by kind of unrecognizable miracle. These mathematicians made these miracles compact in one line. And it's very interesting to see it. If I have 2 minutes, then I will go through this one. Okay, but now we would like to add electromagnetic field to this Hamiltonian. That's result to the Lorentz force in the right-hand side of the Euler equation. It's not isolated system. It's a system driven by electric and magnetic field. And the result of this additional force is simply changing momentum to canonical momentum by shifting it by gauge potential. And then you immediately, by repeating these arguments, you immediately obtain conservation of helicity, but now written not through kinematic momentum, but through canonical momentum. It's also conserved. But that object is not physically, doesn't have physical meaning because it's not gauge invariant. Momentum is gauge, kinematic momentum is gauge invariant. Canonical is not. If we change A by a gradient, the canonical momentum also change by a gradient, and its vorticity doesn't change, but it stays naked here. So this object simply changed by gauge invariant. It's conserved, nevertheless, but that makes sense. However, this object could be, and it's written through canonical kinematic momentum in this method. However, this object could be sort of rearranged and such that it will be gauge invariant, and the price of it is adding to it magnetic field convoluted with momentum. From consideration of non-physically, non-gauge invariant helicity, but pneumatically concerned, we can obtain for that quantity equation which is precisely the same as anomaly in quantum mechanics. And if I think for a minute that fluid could be quantum, then the coefficients will be simply identical. So it will H bar appears here, and it will be identical to quantum hydrodynamics. Not only to okay, quantum mechanics provide a scale, one constant, and this equation can be rescaled. But once the scale is fixed, it cannot be rescaled. And if you put all pieces together, it will be identical as in field. Okay, so as a result, we have the following summary. Axial current in quantum electrodynamics. Number of left movers minus number of right movers. Axial current in fluid mechanics. Helicity corrected by magnetic field. Both objects obey the same equation with coefficients, parameters, everything the same. So what this object means? It means that if I take a fluid, and consider two vortex loops. That's vortices. If the fluid has no boundary, if its manifold has no boundary closed, then vortex lines must be loops closed. They can. Now I put this fluid, classical, ideal fluid. Put the fluid in magnetic field and consider lines with magnetic fields, so of magnetic tubes. This is magnetic field. Now it's in my hands, the fluid in external fields. Now I come to the machine which produces magnetic field, turn some handle, and make these loops linked. And see what happens with my fluid. And what happens with my fluids, the vortex line follow and also linked. That's the essence of the story. One linked number equal to another linked number. Same in electrodynamics. That's a summary. So that's the interpretation of this equation, and it's identical. In quantum electrodynamics, interpretation was that if I put left-right particles, Dirac particles in magnetic field, and then by hands make magnetic loops linked, right movers change to left mover. And here I do the same process and look for vortices, and they unlinked, 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 and then decided to link. And then stay this way before I turn this apparat handle lever back and unlink it. Then they unlink too. So they go kind of two topology goes together. That's a property. What this property offers? You may ask, in quantum electrodynamics, it's all happened because we have Fermi statistics, Pauli. Where it is here? Where it is in water, which we going to encounter cleaning our hands. It actually says that there are processes in water which resemble Fermi. And tornado is actually this process. But tornado has too many Fermions to recognize. But there are more delicate processes in fluids which simply resemble Fermions. What does this mean? It means that fluid is a Hamiltonian system. It has an action. I may consider action. And then I consider action for one flow computed. And then I change the flow, reducing some, I will explain what. And then notice the action changed by 2 pi h bar. And that's fair. So like in Ising model, there are special configuration of spins which resemble Fermions. Apparently it's happened in fluid. And what is drawn here is so-called corona mass expulsion. That's a sum, CMA. And sometimes extreme flux of matter goes out and it come back because there's no boundary to matter. And it twists. Every twist is half Fermion. By this I mean that if you compute the action of this process, this is simulation, but it's real. It's taken from astronomical data. If you see this twist drawn, it's always twisted. If you take an action of this plasma before corona mass expulsion and after corona mass expulsion, the difference between this action will be number of twists times pi times circulation of the vortex around the vortex, which is precisely what we mean by Fermi. And so
Okay.
So I have a question about this last one. In the quantum field theory, it's the path integral measure that changes, gives rise to the anomaly. So you're saying that the same thing happens there for the classical action? It's the path integral measure that changes over the classical variables?
yes, interesting, right? Of course, I thought about it and thank you for this question.
But that's what happens.
But this is what happens.
It's exactly the same. The measure is not invariant and leads to this extra.
Yes, but because it's classical, we operate with differential equation, right? And it's not clear what's a metric in the space of different flows. There are too many flows. But and how to reformulate this question from measure to these flows is quite interesting. I'm not very fluent. I don't understand it very well, but that's what happens.
The reason I'm confused is because in quantum mechanics, it's there's a bunch of paths, right? You go across all paths, but in classical physics, it's just one path. So
but many different initial values.
I see. So that's how you
Solving differential questions.
That's how
We actually consider ensemble of all possible flows.
I see. That's how. Okay. Thanks.
I can put it maybe just one. Maybe I can put it in a different way, but it's very interesting question, how to understand anomalies. In quantum theory, we know that anomalies comes not from the form of the action, but from measure. Measure represents Hilbert space. Right? So it's property of Hilbert space. In fluids, role of Hilbert space is just collection of flows, many different flows, entire space. You may consider motion in the phase space, and that story tells you that some corners of the phase space are not achievable. There is no initial data which bring you to this corner of the phase space. I don't know how it's identified. And that means that part of the space kind of excluded. And the eventual results gives the same result, but it's not much I can say. But good, it's a good point.
Alex,
I wonder if your magnetic field and electromagnetic fields are completely external.
External. I
You
forgot to
don't
say.
put it,
No,
your
no. If you
currents
yeah.
in the Maxwell equation.
Right. If you do that, that will be called magnetohydrodynamic,
Yes.
MHD,
Yes.
magnetohydrodynamic. In my story, the field is absolutely external. The field is completely external. Like in QED, you study kernels in external magnetic field, electromagnetic field, right? You don't include Maxwell interaction, Coulomb interaction. We may, but anomaly comes with the field is external. Right? And such setting is possible in astrophysics, not a problem. Sometimes it's just corner of scale. What
If you
magnetohydrodynamic.
make it self-consistent, your conservation remain or not?
Many things happen. People don't really. Magnetohydrodynamics is too complicated. But some remnants remain, but it's due to many others. So I can tell.
At some point, you mentioned that the Euler equation is written in terms of differential forms, so it doesn't care about the metric. But at the same time, the track equation we have the gravitational anomaly, right? So
Yes, there is a gravitational anomaly here, right?
yeah.
The equation, of course, cares about it.
Mhm.
But that object which we study, written entirely in terms of differential forms, and it doesn't care about metric. But the equation itself, of course, it has metric, it has stress tensor, it's a method, right?
Yeah.
Motion of fluid in the curved space is very different than in a flat space. Of course, equation knows about metric, but that interesting object.
Okay, but I guess in that case, you should also have some non-conservation of the helix, right? Because the Dirac equation case, you have this other dual. Like the Dirac equation case, the actual current it's not conserved.
Is not conserved, right?
In the presence of the half space-time. So you have some analogous effect.
Yes. So the question is, if I understood you correctly, is you're saying the following. If I think about QED, there are many other anomalies. First of all, there is in QCD, there is non-abelian anomaly.
Yeah.
And also there is a gravitational anomaly. And then there is a mixed anomaly.
Yes.
So
my question is more like, do you also see some, analogous effect in this Euler equation?
Right. Here's my answer. I'm looking for it. I don't find it.
Okay.
But I'm pretty sure that it's a new subject. It's simply in progress, but it's a great question. So gravitational anomaly, there are mixed anomaly and gravitational anomaly, right? They're two different. Mixed anomaly probably will be found in the classical equation. For gravitational anomaly, it goes in the next order of derivatives, probably in the quantized Euler equation, which doesn't exist. Quantization of Euler equation is not known. Right? Euler equation, fluid, is the only Hamiltonian system which defies quantization. Even gravity could be sort of quantized, but not too nonlinear.
Yeah, so to define a self-linking number of a single loop,
Mhm.
you usually need to specify a framing of the loop so that it's well defined. But in these classical examples, do you get an effect when you have a single loop which has some self-linking? And if so, does it depend on some choice of framing in the classical description?
Yes. And this experimentally even studied that.
Studied the framing dependence.
They studied the framing data. It's in hydrodynamics, it has its special word, which I forgot. There is a linking, and I forgot there is a special word which instead of framing, and it's very experimentally studied. So this helicity is a sum of framing and linking, and they managed to separate these two, sum up, experimentally distinguished.
Oh, no, it's okay. Done? Okay, we are. Thank you very much.
Which is